This talk started as my lowest expectation, only because it was like a CTF tool. And so on the review board, we were like, yeah, like it's talking about it's a CTF tool, and it actually became at least one of my top 3 favorite talks, if not higher. It's fantastic. This is a really, really cool tool. I'm going to go outside and go yell at everybody who's out there if they're getting coffee still and tell them to come back in, because they need to see this. This is a fantastic tool. It's a fantastic talk. Please welcome Andrew to the stage.
Thank you very much for the very nice introduction. My slides are not up. Oh, yeah. Huh. I see it. All right. So first of all, a little bit about me. So I'm a CTF player. I play with PvP or the super team MMM. Mostly do binary exploitation and reversing. Currently, my day job, I am an auditor at a company called OtterSec. Before that, I was a PhD student for a few years. If you want to reach me, the slide has a few places you can find me. If you find me after the talk and you really didn't like the talk and you want to ask me about something else, I would love if you asked me about symbolic execution or stat solvers or my favorite undefined behavior. But really, none of that matters because for the sake of this talk, I'm just a CTF player, and this talk is about a tool that I wrote primarily to help me solve reverse engineering challenges in CTF. So if you ask a binary exploitation or a reversing CTF player what tool they use the most, they'd probably tell you about pwntools. I'm guessing most people have seen this before, but if you haven't, basically it's a Python library that lets you fork and exec a process. You can do I/O, so this receive until call will block until the process sends you a particular string of bytes. And then when you're done, you can just be Pyda interactive, and then you're just it'll pipe I/O from you to the process as if you had just invoked it directly. Now, the thing about this, though, is that it's completely black box. You can't really do anything to look inside the process and see what's in memory or what's in registers. So if you watch professional CTF players, this is a video from live CTF. So one of my teammates here is playing, I believe, in the live CTF finals. He's solving some kind of binary exploitation challenge. And on the left, he has Python and pwntools, so the tool I just showed you. But on the right, he also has a debugger open with an extension called pwndebug. And the thing about this is that he needs some way to look inside and see what the process is doing, but he actually needs 2 sets of different tools. And I find this to be not exactly ideal. So it turns out you can actually combine this into one script. So if you use pwntools, you probably know this. You can use gdb.debug. You can put your little GDB script straight in your pwntool script and sort of set breakpoints and have it do things and change program behavior while also still maintaining the ability to do send line and receive line. But I find this to be a relatively I don't enjoy using this interface. It'd be really nice if there was some way where we could only write a single script and accomplish both tasks, be able to interact with the process through these do I/O with the process and also see inside it. But it's not obvious what this should look like. So this begs the question of how should we look inside a program at runtime? So there's obvious existing paradigms. So you have debuggers like GDB. So you set breakpoints. You can run commands to handle those breakpoints. And you have hook-based dynamic instrumentation frameworks like Frida. And in theory, with Frida, I'm sure you're all aware, but with Frida interceptor, you can hook any instruction and there's get a JavaScript function that'll run whenever that instruction is reached. Now, in theory, anything you can do with Frida, you can also do with a sufficiently complex GDB script, but no one I know really likes writing really complex GDB scripts. So really, I think this leaves something to be desired. So I'm not really happy with either of these things. Really, my wish list would be I want something that lets me write concise scripts. I don't want to have to wrap all my pointers and strings just because JavaScript doesn't have real integers. I want to be able to do I/O. I want to be able to do send line, receive line, and do this in a single script. I don't want to just have to have a separate script that wraps GDB or wraps a process running under Frida just so I can interact with it at the same time. And I want to be able to reuse packages that I already know. So ideally, all the Python packages that I already use in pwntools, I'd like to be able to still use. So I don't want to have to learn a bunch of new APIs to look up where symbols are in a module, for example. And ideally, I would have something that's like reasonably fast. So I mean, GDB sets like a really low bar here because like it has to go all the way to the kernel to take an interrupt and then notify you of it, and then starts running commands. But ultimately, like I do care somewhat about performance. So the other question that you have to ask if you're like trying to design some kind of interface for interacting with programs is like, do you want something that an API that appears to be blocking, or do you want to just like register a bunch of events and have those events like invoke some function? And like we can see like both of these paradigms kind of exist. Like you have pwntools where like you call receive until and it literally blocks until the process does something. You have like a bunch of GDB commands like finish that'll like block until the process finishes running a function. And these all sort of like appear to be blocking, at least from like the programmer's perspective. And then you have like stuff that's like purely event-based, where like if you use Frida interceptor, you just register a bunch of hooks, and then they run when the process reaches whatever point you desired. And like that's basically all you do. And my answer to this is like, ideally, I'd use both of them, because there might be some circumstances where I'd really like to like block until like use the blocking APIs, and sometimes I'd really like to also like register hooks and have them run. So I'd like to kind of be able to interchange these. So I guess what I'd like to have, and what I tried to build, is this sort of is sort of like both interfaces in one. So like first of all, what I'd like is like something pwntools-style, where you just like make a process call to get some kind of handle, and then you can register hooks at any instruction that'll, and you pass like the address and and some Python function. And those Python functions can make arbitrary modifications at any instruction, so they can modify registers, memory, whatever. And like you would invoke this sort of in a similar way to Frida, where you pass like the name of the script and then the program and the arguments to the program, and it would just run. But at the same time, I would also want to be able to do like use the same pwntools-style APIs that I'm like already familiar with. So here we have like again, we're still using process, but like what I'd like is for process to still behave like a pwntools tube, meaning it has all of the same tube APIs like receive until. So what I want though is I want when you do a receive until, I want it to like actually stop the process at the point that it sends me matching data. So I want to be able to like make modifications after the receive until runs. So the receive until waits until the process sends me the data I want. Blocks, I can make changes to registers, and then I can tell it to continue, maybe run until another PC. And then finally, when I'm done, I can just say run, and it'll run to completion. So this all begs the question of like, how even are you going to implement this interface? I think there's like two main possibilities. Yeah, and I want all of this to be like interoperable with all of the event API I showed before. So like you should still be able to register hooks, and they should still run, even if you're using the like Pyda receive until blocking style stuff. But this begs the question of like, where should the instrumentation actually run? So I think there's like two options. Like you can do something out of process, like GDB or BPF trace, or this like cool library called libdebug. If you haven't looked at it, you should check it out. And basically, you can debug anything that like has a GDB stub. So this lets you debug like stuff that's running on a weird architecture or something that doesn't match your host. But the limitation is that it's like the instrumentation you can insert is like relatively limited. Like you have to, you only really set breakpoints and handle an interrupt when a breakpoint is reached. And that may even require going like outside of your machine. Like you can debug something running on a remote machine with GDB. But this is like also like greatly limits performance, because you actually have to like take the overhead of taking the interrupt every time you hit a breakpoint. The other paradigm is like in process. So this is something like Frida, Intel Pin, or DynamoRIO. So with these sort of tools, your instrumentation can like directly write to memory and change registers, and you can basically modify the application to like say directly jump to your instrumentation, and like this is what Frida interceptor does. But the downside of this is that like your application and your instrumentation have to like actually share OS resources, because they're literally running in the same process. And sometimes that means they also have to share shared libraries, and this can make things kind of complex. But this is the paradigm that I chose, mostly for performance reasons, and mostly because like as a CTF player, like most of the challenges that I run are like normal X86 or ARM Linux challenges, and I'm not super interested in like obscure architectures. So then, within that in-process paradigm, like the question is like, how do you actually implement this API that I want? So like the obvious thing to do is to use an existing dynamic instrumentation framework. So there's several existing tools that already kind of call themselves this, and they're basically anything that provides like an interface to observe and modify the behavior of a program while it's executing. There's sort of two paradigms. You can have probe-based instrumentation. So this is like Frida interceptor. And basically what it does is if you have a function with a bunch of instructions, and you want to have some function that runs when a certain instruction is reached, you basically pass that instruction to replace it with a jump. It jumps out to the instrumentation. You do whatever you want, and then you run whatever instructions that you might have overwritten before jumping back. And the thing about this is that at this boundary, you have to like save and restore basically all registers because the instrumentation can do like arbitrarily complex things, like jump out to V8 and compile some stuff and then run it. Or I guess in our case, maybe we want to do some call into Python. The other paradigm is dynamic recompilation. So this is like what Intel Pin and DynamoRIO do. So basically, what they do is they take every basic block and they give your instrumentation a chance to, or they give your tool a chance to add instrumentation. And this can be like as simple as a single instruction, or it can be as complex as like inserting a call and saving all the register state anyway. But the thing about these tools is that it gives you substantially more flexibility in how complex your instrumentation is and in the overhead that is incurred. But the downside of these tools is that it's a lot more difficult to actually use them. Like the interface is like much more fine-grained, and it's also like usually you have to end up writing a bunch of C and recompiling it every time you want to change your instrumentation. But this is the I chose to base my tool based on DynamoRIO because it allows us to insert more granular instrumentation, which we'll use later. Okay, so now I'm going to talk a little bit about like how did I actually implement this API that I wanted on top of DynamoRIO. And some parts of it are straightforward. I'm not really going to talk about. But the part that's not straightforward is how do you implement these blocking APIs. So like we have this p.receive until call, and basically the way we want this to work is we want that we'll run the process until it reaches a write syscall, and then we'll check and see if the data matches, and then we want the process to stop there, and we want our Python code to run if the data matches. So how is this actually going to work? The way I implemented it is the Python code, your script, actually runs in a separate thread from the application. And so initially, what we do is we allow the Python thread to run until it reaches the first call that yields to the application. So in this case, the first call is the receive until. And then we allow the application code to run. It runs until it reaches the write syscall, and we instrument the write syscall so that we know when it's reached. When it's reached, we then yield again to the tool thread where it can then check to see in Python, does the data match what we're looking for? If it doesn't match, we'll go back to the application. And then we might do another write syscall. And then we'll check the data again, and maybe this time it does match. And so this time, the Python code will continue. So they might choose to change registers or memory. In this case, they'll do a sendline call, and then eventually they'll hit the run until call. And so this is again a yield to the application thread. The application thread will then run some code. And the interesting thing is that we actually allow Python code to run in the application thread as well. So if you had registered a hook before, like suppose you had registered a hook at 1333, which I don't have shown here, but if you had registered a hook, it would run like as sort of a native call in the application thread. You don't have to take the overhead of like doing this sort of yielding between threads. But then eventually the hook returns, you go back to application code, and eventually you reach the PC that was passed to run until. And then the Python thread runs some more. It reaches the final p.run call, and then it just runs all the way to the end because p.run always runs to completion. So at this point, the application will run until it exits. So what does our tool actually have to do here, like on top of sort of what's already done in the dynamic instrumentation framework? Basically, at every exit from Python, so like after every green block, we allow you to modify registers, add and remove hooks, and redirect execution. And so basically, if you do any of these things in your Python code, we have to forward that properly to DynamoRIO and let it know of these modifications. And we also have to handle like a bunch of like other weird events. Like if you create a new thread, we actually give you the opportunity to hook that as an event in the tool. And additionally, if you like hit a seg fault, we'll raise that as a Python exception so you can handle it if you want to. Okay, so what can you actually do with this tool? And this tool is called Pyda. I don't know if I said that, but it does exist, and you can actually do things with it. So here I have an example where we implement like ltrace. So you're just going to print out a trace of all the library calls in a binary. And we did this in about 20 lines of Python. So basically, here I'm using like an existing library from pwntools for parsing an elf. I enumerate all the imports, I hook all of them, and then I just print out each of the function names and each of the arguments. There's a slightly more complex version on GitHub that like also checks whether each of the arguments is a pointer, and it'll like print out some bytes if it is. This next example is a little bit more complicated. So in this example, what we want to do is we want to record all of the indirect jump sources and targets. So the use case is like if you have some sort of obfuscated binary and binary ninja can't recover all of the indirect jump targets, you can basically run it, collect them all, and then tell binary ninja about them. So what I'm doing here is like I'm being kind of lazy, and I'm literally just like processing out to objdump because like that's the quickest thing to do. And basically, we do a bunch of string parsing to figure out like where are all the calls, what are all the arguments to the calls, and then we just store it to this big global. So we register a hook at all of the call locations, and in the hook, we basically store it to a Python dictionary, every source and every destination. When we're done, we just print it out. And after you print this out, you can very easily just like copy paste this into Binja and call add user code ref, and now Binja has all the xrefs. So I thought this was like a relatively short way to do something that I think would be otherwise relatively difficult to do. This next example, if you've ever written a heap exploit, you may appreciate this. So here what we actually do is we actually allow you to use some APIs from pwntdebug directly. So here I'm using the pwntdebug.heap.current.tcache bins API, and I think this is mapped up to some pwntdebug command, but basically you can invoke this and it'll give you a list of all of the active bins, and you can traverse the linked list for each of the bins. And basically what we're doing here is whenever a pwntdebug tries to use a GDB API, we're like pretending to be GDB, and just like if it does a memory access, we just like do the memory access directly. So we have this like little compatibility layer that lets you do use a bunch of existing tools for like heap exploration. And so like if you run this, you can like at any point in the program just like list out the heap state. Okay, so now we get to maybe the cool part. So that was all great, but all of those examples, like the Python hook has to be called like from application code, and when we do that, we have to save the entire register state on both sides. So we save it, and then we do the Python call, and then we restore it. We can actually do a lot better if we make a small compiler that inlines the instrumentation that we want. And so the way this is going to work is instead of calling p.hook to register a hook, we're going to call this other function p.builderHook. It takes the same two arguments, but this time the function that is only called once at instrumentation time. So when DynamoRIO decides that it wants to instrument a basic block, it'll call this function, and you can add whatever instrumentation you want. So in this case, what we're actually going to do is we're going to use Python's ctypes module. And I have this I built a little wrapper where you can put any ctypes type inside this global class, and then we override a bunch of operators. So you can do something like counter.val plus equals 1 to automatically load the value from a ctypes object, increment it by 1, and then store it back. And so the end result is what we're going to do is when we run this function, we generate some IR, and then this IR is then used to generate assembly, which we pass to DynamoRIO, and then DynamoRIO inserts this into the basic block stream, or the instruction stream in the basic block that you specified. And then at runtime, you can it doesn't actually have to incur the overhead of going out to Python. So this is actually a lot faster. Yeah, so the address you see here is actually the address of that ctypes long. And it turns out if you do this, it's substantially faster than incurring the Python call overhead. So here I compared several different tools in terms of overhead over native. So Frida interceptor JavaScript hooks have 75 times overhead. If you this is what I did is the program just makes 10 million hooks where they each increment a counter. And so basically, if you incur the Pyda overhead, if you incur the Python the overhead of calling into Python for every hook, it's 100 times slower, but if you do the inline instrumentation, it's less than 10 times slower. And then I finally have this this final example where instead of just being a single ctypes integer, we actually have a ctypes array. So what you can actually do is you can basically create a ring buffer of the last, say, 1,000 calls to a function, and you can record say the arguments to the last 1,000 calls of some function. And you can do this without ever having to actually call directly into Python. So basically, we wrap the array in a global, and then this global type implements the subscript operator. So you can basically take your counter, mod it with 1,000, and then end up with this ring buffer of the last 1,000 arguments to this function. OK, and now I have a demo. We'll pray to the demo gods. OK, so I'm going to be solving a challenge from CTF. This was Seesaw CTF, I believe, last year. OK, so it's just like the program asked for a passphrase or something. OK, wrong passphrase. So it turns out if you look at the program long enough, you can figure out that it has some sort of side channel. And basically, there's this PC that if we count the number of times it is reached, it should tell us, it should allow us to brute force the flag byte by byte. So all we're going to do is we're going to finish this Pyda script so that we count the number of times that a particular instruction is hit. So in this case, so I already have the process call, and I'm already loading the elf with pwntools. So all we need to do is write the hook. So it's, OK, we want a counter, and we'll global counter plus equals 1. And then we need to register the hook. Side channel. Nice. OK, so and then I think we need to print out the counter. OK, so in theory, if we do this and we run Pyda, and then we type in some password, it should tell us the number of times that the side channel says. So this, in this case, it says 1. And I think the first character of the flag is a W. So if we type a W, OK, so now it's 2. And so I'm actually going to, OK, so at this point, what you could do, you could write a Pyda script so that automatically, when it reaches the end of main, you have it jump back to the beginning of main, and then you can sort of not have to rerun the program every time during your brute force. You can make it loop upon itself. But I'm kind of lazy, so I'm actually just going to write a wrapper that goes around this Pyda script and automatically just invokes it with a different byte until a different byte for every index until we get to the one that causes the side channel to increment by 1. So I actually already have a wrapper. So in theory, it'll print out the passphrase, but you can use your imagination. I won't spoil it. OK. I went kind of fast. So this is the end of my talk. So in summary, this is a tool that I made. You can find it on GitHub. It's called Pyda. And basically, you can register hooks at any instruction. You can use pwntools APIs alongside it. It's based on DynamoRIO, and we have a custom compiler that lets you inline instrumentation. It supports X86 and ARM64 on Linux. I'm working on macOS. If you want the slides, they're in the lower right. If you want the GitHub, it's in the lower left. All right, I think we have a lot of time for questions.
Good. We're OK with having breaks, I was telling you. So first of all, round of applause for a very cool tool.
So you mentioned macOS is a work in progress. What have you found that's different on that platform versus Linux? Because I work a lot on macOS, and I understand the binary format is different, but it just uses ARM instructions. So what have you found?
Yeah, that's a good question. So DynamoRIO does not currently have good support for macOS on ARM64, and that's the part that's mostly work in progress because I'd like to run native applications on my ARM64 Mac. The primary barrier there is primarily you have to deal with hooking system interactions, such as if you spawn a new thread, we need to actually take over the thread so that it runs the instrumented basic blocks instead of the normal ones, and that code just didn't exist. So a lot of it's just OS interactions and not so much the architecture. Although there is some thread local storage stuff that's different. You can't directly set the thread storage, the thread register on macOS ARM for some reason. So you have to go through some syscall. But
you see, I've been into macOS internals, and it has a very interesting way of handling threads and stuff. But yeah, thank you. Thank you.
Oh, you got to make me run, Doug. All right, I'll get over there.
All right, first off, very cool tool. It looks very thoughtfully designed. Can you tell a little bit more about how the hook compilation works and how that goes from Python into C, or into assembly?
Yeah, the short answer is we actually execute this function once to basically build the AST. So the way to think about it is that if you I guess this example, you use b.regs.rdi, that's not a concrete value. That's not an integer. You can't print it out. It's this abstract value. And we basically build an AST by overloading all of the Python operators and then running it once. And then we just yeah, so like right now, like if you look at the code, it's like really bad. This is not optimized at all. Like literally every value takes a single slot on the stack. So like the assembly generation is very straightforward. Like there's no register allocation. Like we're not doing any optimization here. But yeah, I can talk more after if you want.
So does that hook into like a Python JIT, or you are getting the Python AST and then compiling it based off the AST?
We're not getting the Python AST, but we are building an AST from running the Python function once, and then and then generating assembly on our own.
It's both the coolest and the hackiest thing about this whole thing, and it was what blew my mind the most too.
Yeah. I didn't really want to deal with Python ASTs. The downside of this is like you can't write an if statement straightforwardly. Like you have to like you can do some sort of like cmove select thing, but you have to write straight line code. Yeah.
All right. Anybody else? Oh, yep.
Jordan's getting his steps in. So I was just wondering, how have you found the difficulty of debugging your like inline hooks, for example, or like what's injected into the target process? Because so for example, I've used Frida in the past, but I've found it to be annoying to debug because it's basically injecting a whole JavaScript interpreter into the target process, et cetera. So I was just wondering how you found that to be.
The short answer is if it doesn't work the first time, you're kind of screwed unless you know about the internals of whatever tool you're using. So if you don't know about the internals of DynamoRIO and this doesn't work, you're kind of screwed. If you're trying to debug your own instrumentation though, like your own inline instrumentation, you can just like I allow you to just insert arbitrary assembly. Like you can just do like, I think it's like b.raw and then like just pass in some like byte string and it will just like insert those bytes. So like you can just put an interrupt there if you want to like see what your generated assembly looks like. But I think the failure mode you're talking about sounds like it's mostly like the tool is breaking at injection time, and for that, like, I don't have any advice.
Anybody else? All right, we got a break coming up. Go ahead and do one last round of applause for Andrew and Pyda.